Between the summer of 1944 and the final months of 1999, a 55-year time window defined the transition of a United States Army Air Force's interceptor from a frontline asset to a subterranean anomaly. The aircraft in question is a Lockheed P-38 Lightning, delivered as a P-38E to LO, and later redesignated a P-38F5LO. Records associate it with Army Air Forces serial number 4-2-12652. On the flight line, it is marked with the prominent nose number 33. This airframe operates in the Southwest Pacific Theater, a demanding logistical environment where high temperatures, relentless humidity, and rough coral or dirt runways degrade mechanical systems at an accelerated rate. In June 1944, White 33 enters the landing pattern at Finschhafen Airfield, known operationally as Draeger Field, on the tip of the Huon Peninsula in eastern Papua New Guinea. On June 6, 1944, during the landing roll, the nose gear strut collapses. The specific cause is not fully documented in surviving public records. The P-38 utilizes a tricycle landing gear configuration which provides excellent ground visibility, but places immense stress on the single forward strut during rough field operations. The nose section of the Lightning houses a dense concentration of mass, specifically 4 50 caliber machine guns, 1 20mm cannon, and their associated ammunition feeds. When the nose gear gives way, this heavy forward section drops violently onto the runway surface. The kinetic energy of the moving aircraft drives the nose into the ground. This impact does not simply scrape the external aluminum skin, it transmits a severe shockwave through the forward bulkheads and twists the underlying structural longerons that form the central pod. The deformation compromises the aerodynamic and structural geometry of the forward cockpit section. Following the crash landing, engineering crews tow the damaged fighter off the active runway for assessment. They must evaluate the severity of the deformation against the capabilities of a forward operating base. Realigning a twisted central pod requires heavy maintenance jigs and significant labor hours to drill out rivets, replace bent structural members, and manufacture new skin panels. In the middle of 1944, the supply chain is already delivering newer, highly capable fighter variants to the Pacific Theater. The mathematical reality of the logistics chain dictates the outcome. The engineering assessment determines that repairing this specific early model Lightning is an inefficient use of limited maintenance resources. The institutional decision is finalized. In the paperwork, White 33 is struck off charge, written off rather than repaired. However, an operational write-off does not mean the aircraft is immediately discarded. In a remote combat theater, a damaged airframe represents a vital supply of spare parts to keep other aircraft flying. Maintenance crews execute a systematic reduction of the Lightning. Fluids are made safe, and salvageable components, armament, protection, radios, and instruments are removed for reuse. The heavy structural stripping follows. Mechanics remove major assemblies that can still be salvaged, engines, detachable wing sections, and high-value fittings, until little more than the center section remains. What remains is a stripped center hulk. It consists of the hollowed-out central tub and the inboard wing sections, still resting upon the 2 main landing gear struts. The tail booms remain attached to the aft section, but the aircraft is entirely devoid of its primary rigid components. By removing the engines and the outer wings, the maintenance crews fundamentally alter the load-bearing characteristics of the airframe. A complete P-38 derives its structural rigidity from the continuous integration of the outer wings, the heavy engine nacelles, and the central pod. Without these components, and the remaining center tub loses its factory-engineered lifting points, it becomes a fragile, open aluminum shell. This dismantle condition sets the physical baseline for the physical object. The maintenance crews abandon the stripped hulk on the edge of Finschhafen Airfield. It sits parked alongside other scavenged airframes, waiting for the end of the Pacific campaign. The fighter has been reduced to an incomplete skeleton, useless for flight but still occupying physical space on the surface of the base. Then, the surface evidence of the fighter disappears entirely. How does an operational airframe vanish into the jungle without leaving a surface trace? At Draeger Field, later recovery accounts describe disposal pits or trenches used to bury multiple stripped fighters, among them 2 Lockheed P-38 Lightnings and 3 Republic P-47 Thunderbolts. This dense concentration of metal is not a formal storage facility. It is a rapid, post-war material disposal measure. As the Pacific Campaign concludes, the United States military faces a massive logistical surplus. Shipping thousands of obsolete, damaged, or stripped airframes back across the Pacific Ocean is economically and operationally unfeasible. The strategic priority shifts from aircraft maintenance to rapid base closure. The institutional decision is disposal on site. Engineering units mobilize heavy earth-moving equipment to clear the airfield perimeters. They dig large, shallow trenches directly into the soft New Guinea soil. And the objective is to bury the metallic remains as quickly as possible, clearing real estate and neutralizing the surplus hardware. The stripped hulk of White 33, sitting alongside another heavily scavenged Lightning named Jandina III, is slated for this mass burial. The engineers approach the task strictly as an earth-moving operation, prioritizing volume and speed over the preservation of the material. A bulldozer blade engages the aluminum structure of the P-38 to push it toward the excavated trench. The physical interaction is entirely destructive. The tractor applies forward horizontal force against a weakened center tub that is already missing its outer wings and engines. Pushing the incomplete airframe across the rough ground strains the remaining structural rivets. The machine shoves the hulk over the lip of the trench. The Lightning slides down the dirt embankment and settles at the bottom of the pit, in an orientation no one records in detail, only that the stripped center section ends up wedged into the soil. Once backfill begins, the physics is unforgiving. Tons of loose soil are pushed in, and over years of rain, settling, and surface traffic, compact into a heavy, wet clamp. Thin sheet metal yields first, so the upper canopy area and other light skin slowly flatten, while denser lower bulkheads and landing gear structure resist longer and stay keyed into the packed earth. In this buried state, the wreck shifts from atmospheric decay to subterranean corrosion. The trench traps tropical rainwater and moisture, an accelerating galvanic attack where steel landing gear components meet aluminum mounting points. The mass disposal pit at Draeger Field is sealed and rapidly overgrown by thick jungle vegetation. For over half a century, the trench serves as an unmonitored repository, subjecting the 5 buried airframes to continuous underground static pressure and chemical breakdown. The surface topology offers absolutely no indication of the dense metal concentration resting tightly below the root system. What remains of a stripped fuselage after 54 years of subterranean pressure? You cannot simply hoist a subterranean anomaly from the Earth if the rigid structural nodes required for lifting were systematically severed 54 years prior. In 1999, an Australian private salvage group using the name 75 Squadron, not the RAAF unit, locates the Draeger Field mass disposal trenches. The objective is to extract the buried airframes, but the physical reality of the site contradicts standard aircraft recovery protocols. The syndicate is not unearthing an intact machine. They are excavating an incomplete, structurally compromised aluminum shell. Using heavy earth-moving equipment, the recovery team initiates the excavation. They strip away the thick layers of jungle vegetation and carefully remove the topsoil to expose the metallic mass. The team encounters the inherited condition of the mass disposal burial. The center tub of the Lightning remains packed tightly in heavy, damp soil, locked firmly into the earth on its primary landing gear struts. The soil compaction forms a cement-like bond against the lower bulkheads. Clearing the surrounding dirt reveals the key handling constraint. The 1944 stripping removed the wing and engine structure that once carried the Lightning's reinforced lift points. The operation now depends entirely on protecting what remains of the center pod. The salvage team faces a highly restricted lifting geometry. The remaining center pod is essentially an open-ended, hollow aluminum cylinder. The excavation crew must overcome the intense ground suction holding the heavy landing gear struts in the mud. If the riggers wrap standard heavy lifting straps directly around the exposed upper fuselage and apply upward crane tension, the weakened center section will collapse under its own weight. The upward pull of the crane works in direct opposition to the downward anchor of the packed mud. Applying asymmetrical force to this compromised tub guarantees catastrophic structural tearing, destroying the exact material the team is attempting to salvage. To extract the artifact without causing further tearing, The crew excavates around the center section and uses custom rigging designed to pick up what remains of the strongest structure. The lift is slow and controlled, breaking the wreck free of the packed soil before it is set onto a waiting transport trailer. The physical extraction from the trench is complete, but the object sitting on the trailer is severely deformed. Decades of static subterranean pressure thoroughly flattened the upper canopy rails and twisted the forward structural members. The fundamental dimensional data required to understand the exact shape of an early F model, Lightning appears completely lost within the crushed sheet metal. How can the necessary aerodynamic geometry be recovered from a completely crushed center tub? The geometry of a heavy aircraft disposal creates a strict spatial trade-off at the edge of the pit. The original disposal crews faced a dimensional problem when burying the stripped Lightning hulk. While the outer wing panels and the engines had already been removed, the long twin tail booms still extended far behind the main central pod. Leaving these aft sections attached required extending the length of the excavation trench significantly, consuming extra earth-moving time and fuel. To optimize the burial footprint, the engineers made a localized, purely functional decision, and the result is separation. At some point during stripping, disposal, or later disturbance, the long aft boom structures become detached from the central tub. When the salvage team excavates the site, they recover tail boom sections from the same burial context, less deformed than the crushed center tub. They carefully extract these thin aluminum structures from the bottom of the pit. The discovery of the shielded booms shifts the wreck's value immediately. The crushed center tub offers little reliable dimensional data, but the boom skins and internal formers preserve the Lightning's complex original curves, rivet spacing, and structural contours. Those less deformed sections become the primary physical templates for reconstruction, so the salvage team secures them alongside the heavy, deformed central tub. They have successfully extracted the required physical evidence without tearing the surviving metal. The operation completes the physical retrieval from the jungle mud, transitioning the artifacts to transport trailers. With the physical templates secured, how would the artifacts bypass sovereign borders? Crossing borders shifts the primary hazard from fragile aluminum to sovereign heritage law. The convoy moves the artifacts from Drager Field to the industrial port facilities in Lae on the northern coast of New Guinea, where recovery becomes an international export problem. To move the bulky aircraft sections across the ocean, the syndicate relies on standard commercial shipping logistics. The dock workers at the port of Lae pack the deformed center section and the delicate tail structures into large steel shipping containers to protect the metal during transit. In late 1999, cargo vessels carry the containers south across the Coral Sea to the commercial port of Melbourne in Australia. This rapid, containerized export route introduces a legal fault line into the recovery timeline. In aviation archaeology, moving an artifact is only clean if permits, oversight, and documentation align with the host nation's rules. In Papua New Guinea, the disposition of war surplus material and heritage objects is governed under national frameworks that include the War Surplus Materials Act, and later oversight reporting raised questions about whether exports of recovered aircraft complied fully with those requirements. The removal of high-profile wreckage becomes a subject of official scrutiny rather than a settled transfer of title. The investigation systematically audits the export paperwork, the port logistics, and the specific actions of the salvage team. The committee formally documents the failure to engage the National Museum and Art Gallery, the primary authority tasked with protecting state heritage. Because the export bypassed this essential oversight step, the legal status of the Lightning shifts from a salvaged historic artifact to contested sovereign property. The physical safety of the aluminum is no longer the primary constraint. The dominant constraint is now bureaucratic. The legal friction creates a severe operational delay. The aircraft sections sit secure in Australia, but the syndicate cannot finalize a clear title of ownership. Without a clear title, the structural templates cannot be sold to an established restoration facility. International buyers require immaculate provenance to justify the massive financial investment required to rebuild a vintage airframe. Furthermore, aviation regulatory agencies demand a fully documented history before they will issue an airworthiness certificate for an assembled aircraft. The chain of custody disruption acts as an absolute legal firewall, paralyzing the progression of the artifacts. From here, The project can move only as fast as the paperwork allows. 14 years define the operational gap between a resolved administrative hold and an active flight line. In early 2002, the legal and bureaucratic barriers that froze the artifacts finally ease. American interests acquire an unencumbered claim to the material package. The sealed shipping containers depart Australia and cross the Pacific Ocean, arriving in the United States for work with Westpac Restorations, then based at Rialto Airport in California. Only later does the project become associated with Colorado Springs. The transition to the United States officially shifts the project from a salvage logistics problem into an intense mechanical engineering pipeline. The engineering team unloads the crushed center tub and the protected tail sections onto the hangar floor. For this early P-38F configuration, the most useful drawings and manuals are fragmented across collections. To build an airworthy machine, the team has to recover geometry from the surviving metal itself and let that geometry drive every replacement structure they fabricate. They rely entirely on the specific structural condition inherited from the mass disposal pit. Because the original disposal crews tucked the tail sections under the main mass, their internal structures remain shielded from the vertical loads of the earth. The Westpac engineers utilize these uncrushed boom sections as strict dimensional templates. They carefully disassemble the thin aluminum components, measuring the precise distance between rivet holes down to the thousandth of an inch. They trace the exact curvature of the internal aluminum formers and record the tapering angles of the outer skin. The twin tail booms on a Lightning dictate the alignment of the entire aft empennage, including the horizontal stabilizer and the vertical rudders. If these angles are altered during reconstruction, the aircraft will exhibit dangerous, unstable flight characteristics. By capturing the exact geometry from the surviving boom structures, the reverse engineering process creates a highly accurate physical baseline. The surviving sheet metal from the tail sections provides the mathematical constant required to reconstruct the missing elements of the airframe. Armed with these precise measurements, the technicians construct custom, heavy steel jigs to hold the new assemblies in perfect alignment. They begin manufacturing new structural members. They fabricate heavy longerons to replace the crushed sections of the tub and form new aerodynamic skin panels for the central pod. While the upper canopy rails of the original center tub were destroyed, the heavy lower forgings that mounted the landing gear struts survived the burial. The engineers clean and inspect these thick components, verifying their structural integrity. The newly manufactured upper bulkheads are then riveted directly to these surviving lower forgings. This process seamlessly blends the original 1944 core structure with modern aerospace-grade aluminum. The physical restoration progresses systematically. The reconstructed center section is slowly mated with manufactured outer wing panels and 2 overhauled Allison power plants. The complex internal plumbing, flight control cables, and hydraulic systems are integrated into the airframe according to the templated dimensions. This meticulous construction phase requires thousands of labor hours to ensure every structural node aligns perfectly and every load path is continuous. On October 29, 2016, the engineering effort culminates on the runway. The reconstructed Lightning successfully completes its first post-restoration flight. The outcome path is an absolute success. The crushed artifacts pulled from the New Guinea mud have been fully translated into a functional machine. By adhering to the dimensional templates preserved by a historical disposal crew, the restoration team successfully returned an early model interceptor to its exact aerodynamic geometry, completing the structural recovery of White 33.